Hello, my name is Andres Martinez Sanchez, and this is a lightweight neighbor averaging technique for reducing systematic variations in physically unclonable functions. The co-authors on this work are Dr. Deva Bora and Dr. Wenji Che. We are part of the Klitsch School of Electrical and Computer Engineering at New Mexico State University. Graduate student at New Mexico State University. I am part of the research group headed by Dr. Wenji Che, and we focus on hardware security and trust, physically unclonable functions, hardware-software co-design, and artificial intelligence security. So a quick outline of our paper, I'm going to start with motivations and background. Some background. Conventional secret generation and storage using non-volatile memories, or NVMs, suffers from physical attacks. Physically unclonable functions, or PUFs, are promising alternatives due to their temper-evident nature and non-volatile feature of secret generation. Randomness is one of the foundations of PUF security, which ensures that PUF-generated secrets are unpredictable. PUFs derive randomness from random process variations to generate unpredictable and unique secrets for each integrated circuit. So on the right side, we have a figure showing the physical layout of one FPGA board, where each RO, or each frequency, is laid on an XY grid. There are two types of process manufacturing variations that are present on a physical FPGA layout. The first one is random variation. This is shown in the figure as the surface roughness. This is ideal for PUFs as they increase the randomness of the data. The other type of process manufacturing variation is systematic variation. This is shown in the figure as the red slope line. This is non-ideal for PUFs as it shows that there is a pattern present in the data. Systematic variations refer to the non-random bias or patterns across the physical chip layout, and PUF randomness is significantly degraded because of these systematic variations as they show a pattern in data that is supposed to be random. Randomness degradation caused by systematic variation will be discussed in the context of RO PUFs in this work. So RO PUFs, or ring oscillator PUFs, response generations works as follows. So we take the counter values of two selected RO cells, ROI and ROJ. These are selected from n number of oscillators. And we compare a pair of these ROs, their counter values, and determine whether the bit will be a 0 or 1 depending on which counter value is higher. So if the first ROI is less than ROJ, then we generate a 1 for that pair. Otherwise, it's a 0. Systematic variations lead to spatial correlations, which decreases the randomness in the data. So along the rho axis, or the y-axis, the RO's frequency tends to decrease as the y-index increases. So we see here y is increasing, but the overall frequencies seem to be decreasing. If we were to take these two pairs, A1 and A2, or B1 and B2, you can see that since A1 is much more likely to be higher than A2 and B1 is much more likely to be higher than B2, both of these pairs will generate a 0 at the same time. This means that the data is less random and non-independent. Motivations. Several works have been proposed to reduce systematic variations by the following methods: either applying polynomial regressions, applying logarithmic and square root based operations, or introducing normalized pseudo-random number generators. However, these proposed methods require either complex nonlinear mathematical operations or statistical computations which inevitably occur significant implementation overheads. So if we look at this figure, we see the original data is shown by a black line. The trend is represented by this orange regression line. In order to calculate this orange regression line, you need to use complex nonlinear operations shown in this red box here. Our contributions are a lightweight scheme, or is a lightweight scheme that requires simple linear operations, which significantly reduces computational and implementation complexity, shown here. So for a single target point, we only need a small amount of data for each target point. Single calculation for a target point, the simple linear averaging operations are shown here, which is much less complex than these nonlinear operations. And in the end, both methods generate a data set that doesn't have a systematic variation. We also evaluated the effectiveness on various response generation coding schemes and evaluated and compared implementation overheads on Xilinx FPGAs. Now onto the proposed method. So an overview of the proposed method. Our goal is to remove systematic variations from the raw values to obtain only random variation. So in other words, to get the random variation, our final goal, we take the raw values and subtract the systematic variation from the data. The upper figure, shown on the right, shows the raw frequency values as a black line and the trend line or systematic variation as an orange line. The lower figure shows the new values in green after removing the trend line from the raw values. In other words, we take the black line and from the black line we subtract the orange line, which are the local average values using our proposed scheme. And when we do that simple operation, we are able to generate the green line, which are the new frequency values after removing the orange trend line. The orange trend line is obtained by calculating the local average value, f average n, for each raw data point, which is f raw n in the black line. So looking at the target point, we have the target point f raw n, shown as this black square right here. We also have the local average point, f average n, which is this orange square right here. So for each point in this data set, the local average point, f average n, is subtracted from the corresponding f raw n to generate f new n, which is shown in this equation on the right. The details for calculating f average n. First, we start with each raw target data point, or in other words, the nth point, f raw n. We then calculate f average n for each f raw n using the selected values that we are going to specify. So the first step is to specify the range of values from the target on both sides. In this example, we're going to select the left distance of 4, which means on the left side, we're going to go 4 points to the left of the target point. And the right distance will be 3, which means we're going to observe the right 3 points to the right of the target. Step 2 is to choose between the two selection methods for both sides, right? So we have two choices. First one is block selection, which is all points within the distance. So our left distance is 4, so all 4 points to the left of the target point are going to be selected in our average calculation. The other option is edge selection, which is where we only include the endpoint in the averaging calculation. As shown here, see we ignore these 2 points, but only select the one that is 3 away from the target point. Finally, we sum all the selected points and average them for f average n. This equation shows all the points being calculated, take the average, and finally we have f average n. In order to remove the systematic variation that we calculated with f average n, we subtract it from the original data and generate f new n. As shown here in this equation, f raw n minus f average n equals f new n. So for our method, we use row-based calculations. So we apply the proposed method to each row on the FPGA, which is 16 values. Since there are only 16 values, let's say that n is at index 15. We cannot go 3 points to the right or 15, otherwise we'll have overflow issues. So to compensate for this, we decrease the distance on the right so that it doesn't pass the right edge. Or in other words, as the target point approaches to the two ends of the row, the two distance values get reduced to make sure that there's no overflow in the row. So in order to make a configuration of our method, we first choose a combination of selection methods. The two selection methods can be combined for both sides to select neighboring points to calculate the local average. So 4 variants are as follows. We can choose block selection and block selection on both the left and right side. This is shown here is variant 1. We can also do edge selection on both sides. This is shown here in variant 2. We can also combine the two methods. So block selection on the left and edge selection on the right, that'll be variant 3. And if we do edge selection on the left and block selection on the right, that'll be variant 4. We also, within these 4 variants, we also have to do a range of distance values. So in our experimental evaluation, we specify a range up to 5 as the distance values on both sides of the target point. On to the experimental evaluation. The dataset we use is the public RO PUF dataset provided by this citation here, which contains 192 Xilinx Spartan 3E FPGA boards. Each board contains frequency values of 512 RO cells implemented across 32 rows, as shown here, and 16 columns. The metric we use to measure the randomness, we use the NIST statistical test suite. We use the NIST statistical test suite for random number generators to evaluate the randomness of the generated response bit strings. The test contains 9 different test suites, and the minimum pass rate for each test is 185 out of 192 streams. So each one of these stars on this test report indicates a failure in the test, right? So since this one right here is 170 out of 192, we get a star. That one did not pass that randomness test. But this one, 190 out of 192, 190 is greater than 185, so that specific test passed. We evaluated the randomness of response bit strings generated by these 3 coding schemes. We did 1 out of 8 coding, which will give 8 adjacent points a 3-bit index. And each of these cells has a different frequency value. We select the index with the highest frequency value and use that to generate 3 bits. For the couple neighbor, we look at neighboring points, and depending on which one has the higher frequency, we're going to assign it either a 0 or a 1. So in this case, since the left one has the higher frequency, it is a 0. For T-sequence coding, we're going to compare, we're going to cut the row in half and compare each corresponding index with each other. And depending on which one has the higher frequency, either a 1 or a 0 will be generated for that pair. Looking at the NIST randomness test results, we first ran the raw unedited data to get a baseline of where the performance would start. For comparison, we evaluated 3 different types of existing regression-based methods. The inline regression applies regression across all 512 frequency values treated as a one-dimensional array. Row-based regression applies regression to each row across 32 rows in the FPGA layout. Another advanced 2-dimensional XY-based regression is applied to the raw RO frequency values in the layout. We report the NIST results for the 3 best configurations of our proposed scheme across 4 variants. Analyzing the results, we saw that the original raw data has 35 failures out of 54 tests for both p-value and proportion. For the regression-based methods, we found that the polynomial regression on all points in line performed best at orders 4 and 5 with only 22 failures, which is still an improvement over 35. The row-based regression achieved its best results at order 1, and it achieved only 16 failures. And finally, the XY-based 2D regression method achieved the best results out of our existing methods comparison, and it achieved only 2 failures at the higher orders of 4 and 5. But of course, this comes with a high cost of computational complexity by requiring this equation right here. Proposed method, of course, we reported the 3 best configurations, and our best results are 11 failures out of the 54 tests. This is better than both inline regression and row-based regression. We're only performing worse than the high order, highly computationally complex XY based regression method, which has, of course, a higher overhead, and we'll go over this later. Focusing on 1 out of 8 and decoupled neighbor coding, we found that our scheme has up to 65 different configurations that achieve no more than 2 failures out of 9 p-value and 9 proportionalness tests. So we see here that there are as many as 24 configurations that are able to achieve no more than 2 failures for 1 out of 8 coding, and 69 different configurations are achieved for the decoupled neighbor coding. So taking a look at the heat map views before versus after applying the proposed scheme. So before applying the proposed scheme, we see that the raw RO frequency values show an obvious bias. Low values are observed around the edges of the FPGA layout, and there are high values in the middle. After applying the proposed method, we see that the values are significantly changed. The values are more evenly distributed across the entire physical layout, regardless where they are located. We implemented this proposed method in the Xilinx Vertex 6 platform to evaluate its implementation overhead. The right figure reports that the estimated equivalent number of LUTs, including those converted from DSP blocks for different polynomial degrees in the FPGA. We see that as the degree goes up, so does the equivalent number of LUTs. In this table, we see that the lower half is summarized by the number of LUTs that each degree requires for its utilization, which is, depending on the degree, in the thousands. The upper half of the table is our proposed scheme, and we are able to achieve all the results for less than 200 LUTs. The lower polynomial degrees of the regression method still require 1,000 to 4,000 LUTs, and the higher ones are 7,000 plus total number of LUTs, which is more than 10 times the overhead of our proposed scheme, which is still under 200 total LUTs and flip-flops and carry. In conclusion, a lightweight technique for reducing systematic variations of PUFs is proposed, which only requires simple linear operations. Evaluation results show that the method provides comparable effectiveness in improving randomness compared with other existing methods. The proposed method has significantly lower implementation overhead, 10 times lower compared to existing regression-based methods. The parameter diversity feature provides flexibility and will be investigated as a potential way to enable a reconfigurable PUF in the future. Thank you. Any questions?